some formula involving x's and y's. That's pretty much what all chapter 8 is about. Chapter 9 is an intro to vectors where they get you to do things like add, subtract vectors, do scalar multiples and magnitudes of vectors. And what else? And questions about aircraft being blown by the wind, or two ferries pulling a ship, two tugboats pulling a ship. And you're being asked to calculate what the true direction of the aircraft would be and what angle it would make. And lastly, there's a whole bunch of questions right at the end of chapter 9 that deal with calculating the angle between two vectors and calculating a thing called the scalar product to do that. So that's kind of what our topics are. Is there any particular questions that you'd like me to go over? If not, I'm going to start with scalar product questions today. And then, you got one? What you got?
Oh, it's like a kind of a quick question that pertains to 9.1. So I'm kind of wondering how I could, like, on the graphing part of question number 1 question 1 for 9.1, like specifically the graphing section, because I was confused because there's two choices. That was like the V was on the top part of the U, and then one was like the bottom part of the U, and I was like, I don't know how the heck.
You pick the V plus U that's the longest.
What?
Because V plus U is going to be longer than the vector V.
I thought they looked like symmetrical.
Well, I'm looking at, if you give me a few moments, I'm going to go in and look at those questions and we can all see what you're talking about, because it sounds to me like it's a very visual thing. So we kind of need to see it, and it'll give us all an idea of what's going on, right? So if you hold on just a few moments, it's in 9.1, right?
Yeah.
Okay, coming up. And there'll be a big picture, hopefully turning up in a second. And there we go. Right.
Look identical.
Right. Let me share a screen with you. There we go. And the screen I'm going to be sharing is this one. Right, you're all looking at, this is basically the question she was talking about, the first one?
Yep.
Right, now let's see, consider the following. Assume that each point lies on the grid lines. Well, I'm assuming that they do. You're going to take these two vectors, right, and you're then going to, let's see, a vector in the plane in a line segment with a assigned direction. In figure 1, the vector U has an initial point.
Okay.
So here's the vector U, right, and it has an initial point A. You see A, it starts there,
Yeah.
and it finishes at B. So if you look at it, the arrow tells you the direction that you're going, and you start at the top of the arrow and you finish at the bottom. So it starts at A and it finishes at B. So that's that bit. Now, here are some pictures of what might be the combination of U plus V.
Yeah.
Right, so here goes. You see this vector U? Can you imagine I drew this vector U? Right, exactly as it is here. See if you could pick up this vector and place it here so it went like this. Imagine it going like this, like that. So I want a vector U and I want a vector V. And then this vector here would represent U plus V. So your question is, how do I know it's this one and not any of the other choices? Because there's 4 choices and they all look sort of a kind of the same, don't they? Right, so here goes. Vector U in red, vector V in red. U plus V is where you start to where you finish, so it goes that way. Red vector U, double the size of it, you get this vector here, 2U. This picture is the correct one. But let's look at some of the ones that are wrong and why they're wrong. This picture here has got the correct U plus V. But do you see the blue vector 2U is not the same as U? It's not parallel to it, going in the same direction. It's slightly off.
Oh, we need it to be parallel?
Oh yeah, if 2U is parallel to U, it means it's just the same as U, right? So in the top of U, but it goes twice as far. So that kicks off this one. This one here has got the correct 2u, but do you look at the u and the v are not, they're both leaving from the same point. It should be u first, and then where u finishes, that's where the v takes on.
Oh, that makes sense.
Right, and this one here is just totally nonsense, so I wouldn't even describe that in any great terms. Does that help?
Yeah, I was just wondering why the difference between the top and the bottom one, because they like look similar, only like.
Well, yeah, if it wasn't for the fact that the 2u wasn't parallel, it would have been identical.
And I'm talking about the top and bottom to the left side, because it's like.
Well, they are the same because they're correct.
Huh? Oh, what?
If what you're calling the top and bottom is this vector red and red,
No,
and this vector red and red.
it's
Talking
the
about the
top choice and the underneath the top choice.
top choice and the bottom choice on the left side.
Oh, these two?
Yeah.
Yeah, the difference between them is look at U and V.
Okay.
U and V are both leaving from the same point. That's wrong.
Okay.
U nose to tail, V nose to tail. That's the right way that you draw vectors.
Okay.
They are like going on a road, and then when you finish the first road, that's where you start, and you go on the second diagonal roads from there. So
Okay.
that's a discrepancy. Okay, give me a few moments to kick out and kick back in to our other screen. Have we any other questions before I start looking at? I'm very bad at multitasking. Doing stuff and having a conversation don't work well for me. Here we go. Is there anything else you want to cover before we start looking at some scalar product questions? Okay, so let's start right at the beginning for scalar products. The first thing is it's got two different names. It's also called a dot product. I like dot product as a name. To me, it makes more sense, but that's fine. Suppose you have a vector u, and I'm going to call its components u1 and u2. And I have a second vector v, and I'm going to call its components v1 and v2. Then the dot product, written as u dot v, is actually a number. We call numbers and vectors scalars. So it's a scalar equal to what you get when you multiply these two together plus what you get when you multiply these two together. So if the vector u was 1, negative 3, and the vector v was 5, 4, then the dot product would be 1 times 5 add negative 3 times 4, which would be 5 take away 12, which would be negative 7. So there's a lot of questions that have two parts to them. The first part is find the dot product, and then the second part says find the angle between them, which they typically will call theta. So can you imagine a general vector u looking like this, another vector over here v looking like this? Then what we call the angle between the two vectors, theta, is represented by that angle there. Now the way this works is that the angle theta has to be between 0 degrees and 180 degrees. Right, let's look at the two extremes. If we call this vector u, and then we have another vector v, when they're parallel to each other and top of each other, in that story, the angle for theta is 0 degrees. You could have a situation where the vector u goes this way, and the vector v, although it starts there, goes in a totally different direction. In this case, theta would be 100 degrees. 180, I should say. So can you see why you can't have more than 180? Well, you might think, yeah, I can. So let's try and prove why you can't. You could have an angle that went, here's my first vector, there's my second vector. I want to find the angle between the two vectors, and you're going to call it this angle. Well, that's not the case. The angle between the two vectors is always the shortest angle between two vectors. Can you see then that 0 to 180 is the worst you can ever get? Now, there is a very special case where the angle between the two vectors is 90 degrees. And I know Daria knows the answer to this question, so she's not allowed to answer it. Does anybody know what you call two lines, or in this case, two vectors, that make an angle of 90 degrees? What do we say about these two lines, stroke vectors? Give me another name for 90 degrees.
Right angle.
Right angled. Perpendicular. And there's a third one, which you will definitely see if you look up textbooks or watch videos. Orthogonal. So if two vectors are orthogonal, you're going to say, oh, that's just a fancy name for right angled. That's a fancy name for the angle theta is 90 degrees. Okay. Just in case you see that term. Well, let's look at that basic question and see what we've got. An example I've got here, the vector u was 1, -3, and the vector v would be 5, 4. And we want to find the dot product, which I've already done. And the answer to that was -7. And now we want to find the angle theta, the angle between them. The formula that you're going to use is that the cosine of theta is the dot product divided by the magnitude of the two vectors. Now the dot product is -7. I haven't got the magnitude of the two vectors, so I guess I should do that right now. 1 squared plus -3 squared is the square root of 10. And the magnitude of v is 25 plus 16, which is the square root of 30, 41. So it's the square root of 10 times the square root of 41. And I'm going to put brackets around that because when you do it on your calculator, you need to put brackets around this calculation or it won't come out right. So I've got -7 divided by a bracket, the square root of 10 times the square root of 41. And the answer I get is a negative number, which is fine. -0.346.
Is there a reason why we have to follow that formula? Like, why is it like the dot product divided by u and v?
That is the formula that you will use. You are told this formula, you always use it. If you're going to find the angle between two vectors, that's the guy that does the job.
What happens if you use code like sine?
No, they don't use sine. If they did use the sine, they'd have to have a different formula to do it.
Oh.
So I guess the cosine formula is much nicer looking than the formula that has a sine in it. Actually, there might even be, although I don't know of it, there might be a formula that tells you what the tan of theta is, but it's probably so ugly nobody wants to use it.
Mm-hmm.
Right. So I got this, Stella. What's my last step? How do I find the missing angle theta? Because right now all I know is that the cosine of theta is this decimal.
Use the inverse cosine.
Okay. So here we go. Inverse cosine. I'm just going to use the answer button so I don't need to type it all again. And the answer I get is 110.2. I'm just going to call it 110 degrees. But 110.2 if you want to be really accurate about it. Almost every question in the last section of 9 is asking you to find those two things. So let me show you, hopefully show you, that that's in fact the case. Right, are you all looking at a page in WebDesign right now? You all seeing the WebDesign page?
Yes.
Good. So I'm going to hit view. Can you see the view page now? What do you see? Do you see the questions? I guess that's what I should ask.
Not the questions, but I can
Okay, then I'll need to go back out and in again. I forgot that it's pernickety about what you can and can't see. Okay, so this time, there we go.
Yeah, you can. We can see it now.
Right, so the first couple of questions, for instance, they're just the general stuff. Now, this is what a standard question looks like. Here are two vectors called u and v. Find the dot product. The answer is 40 degrees. And find the angle, and it ends up being 54 degrees. So can you imagine that we went through the same process that we did there? We'd find the dot product, which is 40. Then we divide it by the length of this guy times the length of that guy. Do the inverse cosine, and 54 degrees, at least to the nearest whole number, would come out. Excuse me. Are we cool? Right, just scanning through these questions. Do you see that question 4 is the same as question 3, except they've written it in this IJI notation thing, which a lot of people like, I don't. So basically, isn't that 1 comma square root of 3? And isn't this negative square root of 3 comma 1? And they've told me that the dot product is 0. I do not need to do working if the dot product is 0. Don't I already know that the angle will be 90 degrees? That's a very special case. If the dot product is 0, the angle will always be 90 degrees, provided none of these are 0 vectors. Question 5, same thing again. Question 6, same thing again. Are we getting deja vu here? That really a lot of these questions are not particularly onerous, right? This kind of question is kind of interesting. It's determine whether the given vector are perpendicular. In that case, don't you only need to look at the dot product? If the dot product is 0, the vectors are perpendicular. And can you see they're using the word orthogonal? And isn't orthogonal, right angled, and perpendicular all the same thing, at least in the context that we use them? Are we good with that? And I'm scanning through these questions. A little bit different in 13 and 14 here. In question 13, they don't want you to find the angle between two vectors. They just want you to find what u dot v is plus u dot w. So can you imagine you find the dot product of these two vectors here? And then you find the dot product of this vector here with this vector here. And then you add the two together, and evidently in this question it's 19. In this question here, add the two vectors together first. That means add these two, the v and the w. And then whatever that answer is, do u dot that vector. And then the last one looks like u plus v, u dot v, that one. So I'm now going to pick a question, something like that one, and I'll call that, as far as I'm concerned, the end of.
How can you tell if it's multiplying or if it's the dot in there?
Oh, okay. You don't get to multiply vectors together.
Really?
So, yeah, you can only do 2 times a vector. You can't do a vector u times a vector v. It doesn't have a meaning in that sense. So you'll never multiply vectors. So if you ever see a multiplication looking symbol, right, that symbol there, it's the dot product that you're always going to do. So there isn't an opportunity. However, if you see 2v, then that is a multiplication. Do you see that they're quite different? That's just a single vector multiplied by a number. These are two distinct vectors with a dot product symbol between them.
Wait, so what does the one number represent then? Like, can you use like a graph, or is it just?
So what does the one number represent?
So when you multiply, when you get the dot product.
Oh, well, there are two different things going on here. If I said to you, what does that look like? And then I said to you, what does that look like? They have totally different meanings.
Yeah.
Right. If you take the vector v and it looks like this, the vector 2v is just another vector twice as long but parallel.
Yeah.
U dot v is just going to be a number.
Yeah. So like, what does the number represent? Like, kind of like.
It doesn't really represent anything specific. It's just a number. But part of that number is part of a bigger equation.
Okay, that makes sense.
That allows you to get the angle between it. It doesn't represent the angle between them, but it's one of the numbers you need to get the angle between them. Because you also need to know this number and this number to be able to get the angle between them. So on its own, it's not very useful, except when it's equal to 0.
Okay. So that number those two numbers at the bottom, that has nothing to do with absolute values.
No, they just use the symbol.
Oh my God. The one question I was asking about the whole airplane weather, the aircraft, that was what I was looking at, because like, what the heck is the deal looking for?
This fella here means the magnitude.
Oh yeah, because I was like, what does true velocity like mean? Like, what are you using that?
But the true velocity just means what's the real velocity. If I was in that aircraft and I had a speedometer and I looked down at it, what speed would I be seeing? That would be that's what the true velocity meant in that aircraft story. Right, so let's do one of those algebra ones. Suppose u is a vector 1, -3, and v is a vector 2, -5. And I'm being asked to find u add v dot product with u take away v. Right. If you add these two vectors together, you get 1 add 2, which is 3, and -3 add -5 is -8. If you take u and subtract v, you get 1 take away 2, which is -1, and -3 take away -5 is like adding 5, you get 2. And now we're being asked to get the dot product. So 3 times -1, add -8 times 2. So that's -3 take away 16. That is -19. So the answer to the question, what does this equal? It equals a number. It doesn't have any particular meaning. It's just a calculation that's using add, subtract, and dot product of vectors. And so the answer ends up just being a number. And that's what you've been asked to find, and that's all you look for. Are we good?
Yeah.
Right. So I wanted to do dot products first. Is there any topics that you want me to do next? Otherwise, I'm going to do one of those wind aircraft kind of stories.
Okay, I have like a quick question. Okay, I hope it's a quick question, not at least. And it goes back to 8.4 again. I'm sorry.
Okay, not a problem. What's 8.4 got?
I was wondering how I was supposed to get to the conclusion at. Wait, where was it? Shoot. I put like a little note at it. Way to. Okay, I got like question 8 because I needed to.
So what do you have in question 8? Tell me the gist of it.
It was like x equals 9t squared and then y equals 27t cubed, and I was like, I thought I was just gonna do the whole substitution, and then I had to look at like the watch it, and it was like not what I did.
Okay, so we're essentially being asked to eliminate the t, which is just a fancy way of taking this parametric equation and rewrite it as a connection between x's and y's. And there are lots of correct answers to this question. There's lots of different flavors of the same piece of information. So that's the first maybe issue. So I'm just writing it back down again here. If I take this guy, you can go x over 9 is t squared. And that makes t, assuming t is positive, the square root of x over 3. You agree?
Yeah.
So over here, I can then do 27 times t cubed. So I get 27 times the square root of x cubed, all divided by 3. So I get, 3 cubed. Whoops. You know 3 cubed is 27. 3 times 3 times 3. So what do I get? I get the square root of x cubed. Now you can write that as the square root of x cubed, and that is one of the correct answers.
That's what I got wrong.
Okay, now here is another correct answer. If I square both sides.
Yeah.
Well, isn't that also correct?
Yes.
But a different correct.
Yeah, that's what the conclusion that they made. They had to like times it by like the y by like itself, and then like times it like by, and then
yeah. To get to from here to here, don't you just square both sides?
Yes.
And I suppose, or I assume that they decided that this was a better answer than that, although I'm not sure it is a better answer, I know it's correct, is that this one had square roots and they didn't like square roots, so they got rid of them. But it doesn't make this one wrong, it just makes this a different version of the right answer. So when you are doing the eliminate t question, there may well be 2 or 3 equally correct versions of what the final answer may look like. And unfortunately, it's beyond our control. The software may only be looking for one of those 3 and doesn't recognize the other 2 as being correct. It doesn't mean you're wrong, it just means the software is not very good at detecting other correct answers. So that's not your problem, that's the software's problem. So you can simply send me an email saying, I didn't get the points for this because I wrote down this, and eventually when I ran it 8 shots, they told me the correct answer was that, and I got 0 points in my homework for that one question. Well, you shoot me an email and I will look at it, and provided what you said was correct, which would be this, I'll go back and give you the point. And that's how the test will work as well. So if you get a question in the test where there may be more than one correct version of the right answer, when I see you're working, that's what I'll look for. Did you give me an answer that is correct, even if it's not the one they were looking for? Okay. Does that help?
Yeah.
Okay.
Like their process was different. They did like what? So they made it so you know how like x equals 9t squared. Though they made like the problem at y, they like kind of made it like.
Yeah, you know you can do that. Sometimes you can make this guy where to get the t from, or you can make it this guy is where you get the t from. Both end up with a correct answer, but they both end up with different flavors of the correct answer. So you may well have came up with another answer, which would have been x equals the cube root of y squared.
Okay.
Which is, yes, is correct, but it doesn't look like the other 2. But the information that is contained in here is identical to the information that's contained in the other 2. So again, you're not wrong. Okay, for our next question then, we are going to look at a story involving 2 vectors, and essentially we're going to be adding these 2 vectors together and So I have a little story for it. I'm going to have a boat this time, ship. We're going to call it vector B. What do we know about this ship? Well, the ship is going to be sailing northeast, which is 45 degrees if you're northeast, because that's east, the x-axis, and that's north, the y-axis. And it's sailing northeast at 30 miles an hour. And then we have a wind, because this is a sailing boat, I guess, and the wind affects it. And the wind is going to be down here. And the wind is going to be 20 miles an hour. And this angle here is going to be 30 degrees. So if you're on a sailboat and you can go 30 miles an hour, or whatever it is, a ship at 30 miles an hour, but you have got a wind vector that's blowing almost south. I mean, that is almost south, right? With 20 miles an hour. It is definitely going to affect that boat. Can you imagine what's going to happen is that the boat's going to be sailing closer to east. It's going to be blown off course. And typically what you're being asked to do in these questions is to find the true speed of the boat. Like how fast is it really going to be traveling? And secondly, what angle will it be traveling at? What's its direction? So we start off by converting the vector of the boat into its component form. So the x component is the magnitude of the vector times the cosine of the angle in between. So I guess in this case the vector is called b, and the angle is 45 degrees. And the cosine of 45 degrees is root 2 upon 2. So that gets me 15 root 2. So I need some more room for this. That's the x component. Let's get the y component. It's going to be the magnitude of the vector b times the sine of its angle. So it's going to be the magnitude, which is 30 miles an hour, and the sine of 45. And that's going to also give me 15 root 2, which means that the vector that I'm calling b is 15 root 2, 15 root 2. That's its x and y values. Now let's look at the wind then. What we got for the wind? Well, it's 20 miles an hour times the cosine of the angle. And the angle is not 30 degrees. That angle there says 30, but the angle that we talk about is the angle it makes with the x-axis, meaning only this piece of the x-axis. So do you see that the angle you're going to have to deal with is 330 degrees? So if I go over here and I find where 330 degrees is, the cosine is root 3 upon 2. So that's going to be 20 times root 3 upon 2. So that's going to be 10 times root 3. So that's going to be the x component. Now you want to get the y component as well. And that's 20 times the sine of the angle, which is 20 times a half, which is 10. Which means that we now have the vector for the wind. Its x component is 10 root 3 and its y component is 10. So in these questions, the first piece of the puzzle is that you need to take the information about the angles and the magnitude of the vector and find out what they would be in terms of x and y components. Are we okay with that process as far as it's gone?
Yeah.
We're good. Okay. So what we now need to do is find what's called the resultant force. What do the two things do when they combine? It's called a resultant force. Well, we take the vector for the boat and we add it to the vector for the wind. In this case, it's going to be 15 root 2, 15 root 2, being added to 10 root 3 and 10. And typically it's round about this point that I use my calculator and turn these into decimals. So if I go 15 times the square root of 2, and then I add 10 root 3, I get the decimal 38.5. So that would be add the x component here to that x component there. Now, that guy plus that guy is next. So 15 times the square root of 2 plus 10. Hit the wrong button there. 15 times the square root of 2 plus 10. And I get 31.2. So we're going to be taking 15 root 2 and adding 10. Have you noticed that I've turned them into decimals now? So we want two things from this. We want to find the velocity of the boat. So the boat's trying to travel at 30 miles an hour, but this wind is blowing against it. So if you want to find the velocity of the boat, and we'll call this vector v then, right? Got to call it something. Then the magnitude of that is the velocity of the boat. So it's 38.5 squared plus 31.2 squared. And here goes. Square root of 38.5 squared added to 31.2 squared comes out at roughly, check that, okay, left, right, that fella. Bit amazed. Oh well, it is what it is. And what's the direction then? The direction is angle theta. And shoot in space. I didn't swear, I said shoot in space. So I just realized why that looked wrong. Remember this guy that I got here? Have you noticed something about its x and its y? Do you notice that should be negative 10? So when I was doing the cosine of 330 there, or the sine of 330, it's negative 10, right? Now that's going to make a big difference because that number there is now going to be 11.2, which makes that number 11.2. So I'm going to redo my calculation. All I did there was annoying, is I forgot to put a negative in where I should have. So 38.5 squared add 11.2 squared. at last. Essentially, I get 40.1 miles an hour. Okay, I can handle that. So what is angle theta then? Well, you get that by using the formula that the tangent of theta is equal to the y over the x. And so theta is inverse tan of y over x. So it's the inverse tangent of 11.2 over 38.5, and the inverse tan of 11.2 divided by 38.5 ends up being 16.2 degrees. So let's see if that kind of makes sense in this picture. I'm going to be traveling about 40 miles an hour. The boat, if there was no wind, would be going 30. The wind is influencing it. Do you see that essentially what the wind is doing is that it's giving it a little bit extra 10 miles an hour. So you're going to travel a little bit faster. So what's the negative side of this? Well, do you know the angle that you're going to travel in is about 16 degrees. So yes, you will travel faster, but won't you be off course by a fair amount? Now, people, question. Have we a question?
Wait, where did the 16 degrees come from again? I'm sorry.
The 16 degrees came from the size, the angle between the two vectors, 16.2 degrees. It came from here. So if I found the angle that the vector v, the resultant vector, makes with the x-axis, it ended up being 16.2 degrees. Which is what my picture here is trying to indicate.
Oh, I see it. Okay.
Right.
Okay. I just blinked out for a second.
So if I was in a sailboat, and I'm sure they did this in the olden days, if I was in a sailboat and I knew which way the wind was blowing, and I'm pretty sure you can figure that out, and you get one of those little hand things that turns, you can actually tell what the speed is. I would be blown off course by quite a lot. So if I was traveling from one island to another and I let the wind keep doing this, wouldn't I miss my island? I'd travel really fast, but I wouldn't be traveling towards the island. I'd be blowing off course, right? I'm not traveling at 45, which is what I tried to do. I'm being blown off course by 16 degrees. Do you know how they figure out how to sail to compensate for that? Do you know what the boat does? It doesn't sail at 45 degrees. It sails at 61 degrees.
Huh.
And why does it sail at 61? So that when it gets blown off course by the wind, doesn't take it blown actually on course. You compensate for the bit that you're going to be off course by when you do your direction. So when aircraft are flying from Seattle to Glasgow, or wherever it is they may be flying to, you'll find very often that what the pilot does is that the heading that they travel, which is basically the degrees that they go, isn't actually the real degrees to the destination. It's actually a little bit more to the north or a little bit more to the south, because they're also calculated into that what the contribution to the wind is to blow off course. So the result is that they actually do fly straight to the place that they want. They just have to compensate for the wind. So it's kind of clever that they do that. Otherwise, what would happen is if you just kept on flying off course, wouldn't you arrive 400 miles south of Glasgow, right? Because the wind is blowing you off course all the way.
Like a sniper.
Okay. Oh yeah, Sniper does that as well, don't they?
Yeah.
Yeah, they have a little calculation thing. I don't quite know the details of it, but they know that if there was no wind, the bullet would travel straight. But there is some wind, and if the bullet's going to be 2 degrees off, then they compensate by shooting 2 degrees in the other direction, and that makes the bullet go straight. at least straight to where they're trying to get it to go. And we are now going to have to close off at this point. So remember, your test is due Friday midnight as always, and it's going to be in chapters 8 and 9.
What section did you did this question pertain to?
Say that question again.
So what, like, the things about the boat did that pertain to 9.1 or 9.2?
Yeah, that was the boat one was a 9.2.
Okay.
Okay. So
you didn't do
bye-bye.
anything about parametric or anything?
I didn't, not this time. If you have any issues with that, you just have to talk to me, send me an email. I'll try and help you out wherever I can.
Okay.
Okay.
Thank you.
Now I'm about to do another one, so if you want to drop in for that one, feel free. You don't need to. It's totally up to you. But I have to leave for my third meeting now, and it's on 1:42 as well. So bye-bye, everybody.
Bye.
Bye.
Thank you.
You're welcome.